This is Einstein's groundbreaking theory that describes how gravity works not just as a force, but as a result of the curvature of space and time caused by masses of objects like planets or stars. Imagine space and time as a stretched out fabric. Massive objects like stars and planets create dents in this fabric, and that's what we see as gravity. A key idea in general relativity is invariance under coordinate transformations. But what does that mean? Simply put, the laws of physics remain the same no matter how you look at them or where you are. It's like saying that the rules of a game don't change whether you are watching from the sidelines or playing on the field. Coordinate transformations are changes in the way we describe the position of objects in space and time. For example, switching from using a map with north at the top to one with the east at the top is a coordinate transformation. The locations haven't changed, just the way we are representing them has changed. In physics, the laws must stay consistent regardless of these changes in perspective. That means if you are standing still or moving at a constant speed in a car or accelerating away in a jet airplane, the physical objects must be the same. Let me explain in an example. Consider this pen. This is a physical object. The length of this pen is independent of how you and I watch it. It will be the same if I measure it while I am running, or when I am on an airplane landing, or in a race car accelerating away. This concept is one of the two pillars on which Einstein established his theory of gravity. Technically speaking, we say the length of this pen is invariant under the changes of observers, and all these observers can potentially carry their rulers to measure the length of the pen. In physics, we refer to these rulers as coordinate systems. So any observer, no matter if they are sitting on an airplane or standing by the side of a road, has a coordinate system attached to them. Einstein's theory of gravity, general relativity, is independent of which one of these coordinates that are attached to their observers is used to study gravity. Technically speaking, the theory is invariant under coordinate transformations. These coordinates, rulers attached to the observers, in gravity are just the columns of a spreadsheet in machine learning problems. We'll get back to machine learning and data invariances that lead to singularities that force us to reduce dimensions later in the video. For now, let's see why we need to reduce dimensions in gravity. Moving from the cosmic scale to the microscopic, we enter the realm of quantum mechanics, which describes the small-scale behaviors of any physical system, including gravity. That means if we want to study gravity at very small scales, we need to quantize Einstein's theory of gravity. One of the earliest challenges of this quantization effort is the subject of this video, and that is the issue of invariance under coordinate transformations that we just discussed. The invariance under change of coordinates equivalently means these coordinates are not all independent. On the other hand, in quantum mechanics, which is the theory of small scales in physics, we are only allowed to quantize the independent variables of a system. So we have to reduce the dependent variables in Einstein's theory if we want to quantize it. To see how an invariance in a system translates into dependence between its variables, let's get back to the example of my pen. In physics, an observer like me can define a coordinate system by holding three rulers orthogonal to each other, and also a stopwatch as the ruler of time. Ruler 1 will make the x-axis, the second and third rulers make the y and z-axis, and the stopwatch make the time axis. The length of this pen is the same if you and I measure it using the rulers in our hands. Now, this property of the pen, whose length is independent of the observer watching it, has another side. It also means that if I measure the projection of this pen on the x and y rulers, I can already deduce the z reading. The reason is that the invariance property is equivalent to having this constraint between the x, y, and z variables. Therefore, knowing x and y, we already know the z variable. Here, each x, y, and z reading makes a column of my spreadsheet, just like in machine learning. And the z column is kind of redundant. In quantum mechanics and also in machine learning, we need to remove this type of redundancy, or in other words, reduce the dimensions of the system. At this point, I want to get into the subject of dimension reduction in machine learning. So let me quickly wrap up the story of quantum gravity. To systematically perform this dimension reduction in Einstein's theory of gravity and prepare it for quantization, Paul Dirac, one of the founders of quantum mechanics, proposed using constraints to reduce the number of dimensions in our equations. That means, just like in the case of my pen, when we used a constraint between the x, y, and z variables to remove one of them, we could eliminate redundant variables in quantum gravity by applying certain conditions to its variables. These conditions take the invariance under coordinate transformations into account. In the case of gravity, unfortunately, even after resolving this issue and despite many efforts, quantum gravity remains an open problem in physics due to other challenges and paradoxes that are not relevant to the subject of this video, so I won't be explaining them here. Instead, let me do a quick recap. In this video, we are going to show the invariance under some transformation will always lead to some redundancy in the variables of a system. And this concept holds even in two seemingly different fields, Einstein's theory of gravity and machine learning. In that case, gravity, machine learning, or any other problem that has a sort of invariance need to deal with a common challenge known as dimensionality reduction. Dimensionality reduction is a method to remove redundancies among the variables of a system that are caused by a symmetry that presents itself in the form of an invariance. These redundancies, if not removed, don't let us derive meaningful results out of the system that we would like to study. Think of it as trying to solve a puzzle by focusing only on the most important pieces. In both quantizing Einstein's gravity and processing large datasets in machine learning, dimensionality reduction plays a similar role. Before I move on, let me introduce our high-ticket bootcamp, a personalized, immersive program designed to transform you into a sought-after data scientist. With daily access to me, we'll build your online portfolio, master job-ready skills, and prepare for interviews. We have limited the spots to ensure the quality. To apply, go to our website and fill out this form. Now let's bridge the gap between physics and machine learning. So far, we talked about invariance and dimensionality reduction in physics. Let's now see how similar concepts apply when dealing with data. Just as physical laws remain the same under coordinate transformations, some datasets exhibit invariance under certain transformations, and this invariance leads to singularities that we better remove to build more predictive and powerful models for our data. To better see what I mean, let's look at this spreadsheet where each row represents a data point and each column is a variable of the system, just like the x, y, z readings from the rulers in the physics example. And here is a visualization of this particular dataset. As you can see, data is mostly spread along an axis. That is the most important principal component of this data. Now, if I rotate the image by whatever angle around that axis, the look of the image wouldn't change much. But if I rotate along, for example, the y-axis, the visual look of the image changes. So here we can say our dataset is invariant under rotation around the main principal component of the data. This particular invariance is such that only one out of the three dimensions, the axis of the plot, is needed to model this dataset. And that would be the axis along which data lies. Now, look at this image. This is the visualization of another dataset. This plot still has an invariance, but with a lower degree. This lower degree of invariance means we need more principal components, in this case 2, to explain the data. To see why we have a lower degree of invariance in this second example, note that the look of the plot will not change if I rotate the image by only 180 degrees along the main principal component. In the first example, I was not restricted to a particular angle, 180 degrees, and I could rotate by whatever angle I liked. The reason I have a lower degree of invariance in this second example is that I have a second important principal component in this case. To see that, note that if I rotate the image by 180 degrees around this second principal component, the look of the image doesn't change. So in this particular case, I only need these two axes to model my data, and the third axis is redundant. Therefore, just like in the case of Einstein's theory of gravity, invariance in the system is equivalent to a redundancy in the variables of the system. In other words, I don't need as many variables as the number of columns of the spreadsheet because there is some dependency between them. But what I just showed is not a practical method to find invariances in our system. So how do we find these invariances in our data? One powerful tool is the covariance matrix and its eigenvalues. Let's first discuss the concept and then we get into the practical part. For that, I'm going to get back to the two plots that we just discussed. I already showed you the important principal components, the important axis of the data in both plots. What do we see in common between these important axes? Data is a spread along them, right? That means data has the highest variance along these axes. Now look at the non-important axis. The invariance of data along them is close to zero, right? These variances along the principal components are just the eigenvalues of the covariance matrix of the data at hand. That means whenever I have a dataset, I can quickly compute its covariance in the way I show you later in this video, and then find the eigenvalues of that covariance matrix. The largest eigenvalue means the largest variance along the corresponding eigenvector, and that corresponding eigenvector is just the most important axis, or in other words, the most important principal component. The eigenvector of the second largest eigenvalue is the second most important axis or principal component of the system. If some of the eigenvalues are very small relative to the large ones, or even worse, are exactly zero, the axes along their eigenvectors are the redundant ones and we can throw them out. Now let's discuss another important concept. So far we have discussed a practical way to find the important axis of the data. But most of the time, the columns of our spreadsheet, which are the original axis of the system, are not along the important axis or the principal component axis. So we need to change our coordinate system. This is the same concept as in the case of Einstein's gravitational theory, where we could choose to express observations in either my coordinate system, my set of rulers, or your coordinate system. And the reality of the system would not change by that transformation. In the case of data, we need to move from the original coordinate system, the original columns of the spreadsheet, to the coordinate system that coincides with the important principal components. So how do we exactly do this transformation? Let's get back to our example plots. Here, these are the original axes or the columns of the dataset, and here are the important axes or the principal components. So all we need to do is to rotate the original axis. The angle for rotation is just the angle between the original axis and the important axis as given by the eigenvectors of the covariance matrix. But don't worry, all these stuff are already implemented and we can achieve them by just 1 or 2 lines of code. Now let's see how we can apply these concepts using some Python libraries. Let me introduce CompuFlair's consulting services offering tailored data-driven solutions like predictive analysis, risk assessment, downtime forecasting, pipeline automation, and customer behavior insights. If interested, visit our website and fill out this form to get started. Here is my Jupyter notebook, and in the first cell, I generate random data to work with. In a real-world project, the data is collected through some experiments or a set of observations. So let's move on to the more important cells. In this cell, I plot every row of the dataset as a point in 3 dimensions. In most real-world problems, the number of columns is more than 3, and this type of plot cannot be used to visualize and identify principal components. So let's move on to the next cell, where we find the covariance matrix of data using NumPy library and then compute the eigenvalue and eigenvectors of the covariance matrix. Here are the eigenvalues of the covariance matrix of the data. As you can see, the first two eigenvalues are much larger than the last one. That indicates that we can keep only the first two dimensions of the principal components and reduce the dimension from 3 to 2. In this cell, I use the scikit-learn library to perform the coordinate transformation. So when I call the fit method, it internally computes the covariance matrix, finds the eigenvalues and eigenvectors of that, and makes everything ready to perform the coordinate transformation. This transform method then converts the original data into the transformed or rotated data. In other words, performs the coordinate transformation. Finally, here is an alternative to finding eigenvalues of the covariance matrix as a method to find the number of important dimensions. The x-axis shows the label of the principal components. The y-axis shows the cumulative explained variance. As you can see, the first two principal components explain around 95% of the variance in the data. So an elbow, like in this case, usually indicates the number of important components that we need to hold. I hope you have enjoyed this video. Take care, and I'll see you in the next video.